Last week, what we talked about is we talked about the thermodynamics. Thermodynamics of defect formation. It's actually ionic defect formation. Okay. So the example we use is basically the formation of a fractal pair, or to be exact, any fractal pair. So again, let me just draw a bunch of ions. So for example, again, this as example, this sodium chloride. So essentially, what we have is we create a chlorine vacancy. Again, this is a covalent notation, and we insert a chlorine interstitial. So this should be positive. Okay, so then if we write in defect chemical reaction, it basically looks like this. So from the state where we don't have any defects to the state we have a pair of defects. Okay, it should be positive. Okay. So we talked about how to predict the equilibrium concentration of a single defect, and also we talked about what if we have the defect reaction, a pair of defects such like this. Okay. So I'm not going to go over everything we talked about last week. I just want to quickly remind you that for a single defect, what we have is we want to know the basic Gibbs free energy, right? We want to minimize the Gibbs free energy of defect formation. And the Gibbs free energy has several terms, right? So if we use small nd as the number of defect we put in the structure, and the big N as all these sites that defect can occupy, then we have two terms. Actually three, right? The first one is the formation enthalpy of a single defect, basically delta small h. Then also we have T delta S, but this S is vibrational entropy. Right, so these two, they basically scale up with the number of defect you have. Then you have another one, which is very important, is comparational entropy. Right, so we talked about how to calculate this one. This is very important. And without comparational entropy, we won't have any defect at finite temperature. Okay, so end of the day, we have the equilibrium number of defects, or equilibrium fraction of defect. Usually we use a bracket. Okay, so it's basically the exponential of the basically you put this here, alright? Defect h minus t. Of course, there's negative sign here and an RT here. Okay, so that's very easy. Okay. Then we move on to talk about what if we have two different kinds of defects. Then we have defect reaction. Then we know the product of the two defects. Basically, the product of the fraction of the two defects will be something like this. Should be exponential minus RT mu 0. Okay. So of course, if we don't have any other defect, we have to have the charge neutrality, right? Then we can have each of this basically divided by 2. Okay. So and also what we can call this the So basically, it can be reaction, or it can be, in this particular case, a fractal pair formation. Okay. So basically, this is evaluated per molar. So it's delta G is actually delta, it's actually mu here, and also it's a standard convention. Okay, so if we plug in this here, it will be mu 0. Okay, in here. Okay, so very importantly, notice that there's 2 here, right? So this is very important because now we have to apply channel neutrality, then these 2 should be equal to each other. Okay. So, and of course, if you like, let me erase this part. If you like, so since this guy, this is the some kind of the Gibbs free energy, right? This is just basically Gibbs free energy per molar. You can further write it should be delta H reaction. Of course, we like to use the standard condition anyway. If you do not remember why it's standard condition, you can check the notes from last class. Okay, then minus Ts. Okay, right. So because this is simply because this is the Gibbs free energy. Okay. So then we can further write one more time. So it's 2R. Because there's T here, there's T here, they just cancel out. Delta S exponential okay. So something like this, no problem, right? So very commonly what we want to do is we want to plot the fractional concentration in log scale. This is the log scale, this one, or it should be equal to log scale this one, right, in this case. As function of the 1 over T. Okay. So then it should be a straight line, right? So we know that in this case the slope should be minus 2R delta H. And here should be basically delta S to R, however it should be exponential. So I think you asked me last class why, I mean, if the delta S is 0, then this thing should be 1, right? Or log this should be 0, right? So this is because usually when we plot it, okay, so this is 1, then we probably have 10 to the minus 2, 10 to the minus 4, something like this, okay? I mean, of course, log 1 is 0, but usually we don't plot that way, right? What we plot is basically plot something like this. Or, so essentially conveniently, basically you can say this is the fraction, but just use log scale for the y-axis, something like this. Okay. All right. So today the first thing I want to do is to kind of make it more general. Okay. So because again in next class and also maybe later we're going to use this more and more often. So we want to use it more general to go beyond just a simple Frankel pair defect reaction. Okay. So the first thing we want to note is that, so this is very similar. Actually, there's no difference between this defect, so basically it's defect chemical reaction. So it's basically a chemical reaction, right? So all the theory about the chemical reaction should apply. So what we know is that this guy, okay, is exponential part, is basically nothing but the chemical equilibrium constant. So this basically K is called a chemical equilibrium constant. Or in Chinese, 化学平衡常数. Okay, so which you probably all learned in your high school or general chemistry class. Okay. So as you can see here, so if we assume this guy is not a function of temperature, or it's not a strong function of temperature, then then this guy, because usually this delta S can be small. Then if this guy is kind of constant, then the K, then K is basically only a function of the temperature. So as you can see here, you have exponential, you have RT here. So it's basically a function of the temperature. Okay. So then all the theory about the chemical reaction equilibrium can be applied. Okay. So if that's the case, let's write it more general. Okay. So basically, we think about a general defect chemical reaction. So basically, I'm getting lazy, so I just write this defect chemical reaction. Okay. So a general defect chemical reaction is basically something like this. Before you don't have any defects, or you can move actually all the reactants or all the products to the other end. Okay, then you form different kinds of defect, right? So it can be mu A plus mu B plus mu C. So I'll explain what it is in a minute, and so on and so forth. Okay. So this since okay. So this mu, or so basically I say mu D is basically the stoichiometry. So what does that mean? So for example, of course here the mu is basically 1. Okay. So basically you can imagine there's 1 here, there's 1 here, right? Of course if you go to more complicated cases, then you do have this different stoichiometry. Okay. For example, so we think about the Schottky pairs in alumina or alumina oxide, then we have to form aluminum vacancy. So of course alumina is 3 parts, so vacancy has 3 negative charge. And oxygen defects, oxygen vacancy, oxygen has 2 minus, right? However, you have to balance this 2, right? So you have to have 2 here and 3 here. So basically the mu aluminum is 2, mu oxygen vacancy is basically 3. Okay. Anyway, you have to have this in to balance the charge. Otherwise, you don't have the defect reaction to be correct. Okay, so then if you think about that, if you let the reaction to go on, right? So let the reaction to basically move this direction by just a small amount, then you have the change of the gives free energy is basically the change of mu A, the chemical potential. Then just you can just go on and write this. Okay. So or we choose to be more general. So or we choose to write it in a more convenient way. We can say this is basically summation of D, mu D. Okay. So basically, you can imagine that you can sum all this into just this is kind of defect reaction. It's okay, right? You know what that is, right? D is just the subscript. In this case, D will be both this and this one. Okay. And if you have more defect, you just keep adding it into it. Okay. Then the DG is basically summation of mu D. Okay. So D is defect. So we basically use this as the subscript for everything. Okay. So we want this to be 0 at equilibrium, right? At equilibrium. Okay. So then can we do? Right, so what we can do is we can just recognize this mu d should have two parts, right? It should have the standard condition and the RT logarithm. Right, so this is two parts. Of course, in this case, the reason we can use this, again, I just want to remind you, there's an assumption with that, this basically dilute limit. Or it's called non-interaction. So basically what it's saying is that the gamma is basically 1, gamma t is basically 1, so which means that the activity coefficient for each defect is basically 1. Okay, so if you plug into this equation, what you can get is, if you get into this one and just do a little bit analysis, basically the first thing is you have this standard part, right? So basically you have the standard part, some d mu d 0. Okay. So this is basically nothing but the same thing as the reaction gives free energy. Okay. So it's the same thing as this one, but now you have more defects. Okay. Of course, here you have to also write the stoichiometry. Okay. And the other part, you have this should be negative. Now you have the RT, right? So basically, I write RT here, and we have logarithm. Let me write it more clearly. We have RT logarithm. Then you have all this d, okay, together. Okay. So all this d together, then you have mu d before the logarithm, right? So together you have it's basically the multiply everything, right? Basically the d mu d, okay. Right? No problem. So finally, what we have is so-called a mass action law. So this actually should be, let me write it more formally. So this big pi means that we multiply everything together. It's basically just like a summation number. Okay. So basically you have d mu d should be exponential minus rt mu fraction. Okay, then it should be just your chemical equilibrium constant. Okay. So this basically gives us a way to solve for everything. So if we have something like this, then we can quickly apply to any defect reaction we have later in this lecture. Okay. For example, I'll give you a case. We'll perhaps talk about this next class, but I just want to show you a little bit. For example, we can have formation of oxygen vacancies. This is an example. Okay, so formation of oxygen vacancies. So if we just think of only oxygen vacancies and there's no other ionic defect, then usually what we write is something like this. So basically we have oxygen sitting in oxygen site, right? So it's just normal oxygen. So of course oxygen sitting on oxygen site, there's no charge. There's no difference charge, right? This is a normal oxygen. Then we can form oxygen vacancy. Oxygen vacancy has two positive charge, right? So if we have two positive charge, we have to charge balance it, right? So here we form aluminum vacancy, right? So which is the cation defects, and we have the negative charge. What if we do not want to form aluminum defect? We can form electronic defect. So this is basically electrons. So actually today the main topic will be electron defect. So we'll get to that part in a minute. I just want to write something like this. So basically this is just an electron, okay. Now of course the oxygen has to go somewhere, right? It cannot just vanish, right? So it turns out oxygen just goes to gas phase. Okay, so the basic gas phase. Okay. Okay, so I mean you can directly write according to this, right? So what you can write is oxygen vacancy fraction, then electron fraction. Of course, notice here we have 2, right? So there should be 1 here, but 1 you just neglect. So we have 2 here, and we have oxygen gas. Okay, for the gas phase we don't use the fraction, we use the pressure or partial pressure, right? Of course, there's 1/2 here, so we have to write 1/2. Okay, so that's not finished because there's another thing here, right? So one way to think of this, you can mimic exactly something like this. Okay, here we have none, there's nothing here. So what you can think of is you move this one here. So you write none here, then minus this one. Okay, now you basically move this here, right? Or you can write, now it's -1. Okay, if it's -1, you just put it to the denominator. Okay. Right, or if you just remember, anything you put it here, you just put it underneath, right? Okay. So then there should be some kind of K, chemical reaction equilibrium constant, right? Let's call it KO. And of course, KO is the function of temperature. Okay, so I think in the next lecture we're going to use it heavily. So I just want to first give you an idea how to write the defect chemical reaction equilibrium. It's actually quite convenient. Okay. All right. Any questions? No. All is clear. All right. This one. Okay. All right. So this is actually a little bit left over from last lecture. In today's lecture, the main topic is actually the, let's say, the formation of electronic defects. So, electronic defects. So we know, although this course is called solid-state ionics, but as I remind you, the first lecture is that although we care about ionic defects, we also need to care about electrons because you have, for most of the things we study, most of the ionic crystal, we have both ionic and electronic defects in the structure. And also at the interface or in the bulk, we have the either reacting or diffusion of both. Okay, so we had to have proper treatment of electronic defects. Okay, so it will be a little bit knowledge on semiconductor physics, but only in the beginning level. Okay, so that so in today's lecture, I'll probably have all you need for my course. Of course, if you want to go on to study more, you can go to, for example, Hongxin and Kongmei's lecture, or other people will also teach about this. Okay. But anyway, so it's important to know that because you can already see in this example, when you form Austin frequencies, you also form electrons, right? You have to know why you have that. Okay. So first, let's see. Let's talk about what is the semiconductor. Okay. So we know that we have metals, right? So so we know that when we form crystals, we have these atomic orbitals. Atomic orbitals, then they overlap each other, they form the band, right? For example, you have this kind of band. So, for example, electron occupy this part, and you have another band formed by orbitals. And for metals, you have the partially filled states. So think about this as this is called bands, right? So our energy bands, 能带 in Chinese. So basically, you have atomic orbitals from this one. For example, so here, if we use the copper as an example, so example is copper. And then this can be copper 1s, so this can be copper 3D. Okay. Anyway, copper 3D is partially filled. Okay. Or anyway, so you can imagine that because it's partially filled, the electron can conduct. Okay. So these things are electrons, or in our case, we like to write as this one. Okay. Anyway, so these are metals. However, in most of the things we study, we don't have metals, right? It's too boring, right? We have semiconductors. Okay. So for semiconductors, things are not that simple, okay? Unfortunately, let me show this a little bit. Okay. For semiconductors, it's slightly different. Okay, for example, so this will be copper oxide. Just give you an idea. So for copper oxide, you are less fortunate because, for example, all these bands are filled, and in reality it can be often 2p, or also in 2p orbital, also in 2p band, and all these 3D bands are empty. Okay. I mean, imagine that for a minute. Then, since everything is full here, the electron cannot conduct. So this electron field. I mean, here is empty. There's no electrons. Of course, you cannot have conductivity. Okay. So that's why in semiconductors you have much less conductivity compared to metal, right? So we all know that. If you measure the copper can conduct electricity, but copper oxide likely cannot, right? So very simple. And of course, we call it, there must be some distance, energy distance between this part and this part, right? So this is called a band gap. So it's called a band gap. Or conventionally, people use EG. I think that's from German, but I don't know why. Anyway, and we also call it, so this part, where all the electrons are filled, we call the valence band. Valence band. Or VB for short. Here we call it conduction band. You'll know why that in a minute. CD. Okay. Of course, you can imagine that. So going up this way, that's the increased energy, right? So you all learn that in your chemistry class, copper wires is lower energy. You fill the copper wires first, then you fill the copper 3D later, right? Same thing here. You fill the lower energy space first, then you go up, and then you go up, and you fill this later. So so it's also useful to know there are two energy at the edge, right? The highest part of this one and lowest part of the this one, right? So this is called I'll write it here. Wave span maxima. Okay. Or VDM. Right, so this is basically the highest point of the field electrons, right? Or if you think of molecular way, or you work with molecular semiconductors, people call it HUMO. So basically, highest occupied molecular orbital. Well, this is some conceptual differences, but it's basically not exactly, basically the same thing. Okay. You can also identify this one. So this one is, as you can imagine, called a conduction band minima. Minima. Anyway, minima. So, yeah. Single. Anyway. So it's called a CDM. Or if you again work with molecules, you will call it LUMO. So basically, lowest unoccupied molecular orbital. I won't write it in full. Okay. Right. So, however, we know that the reason it's called a semiconductor is because it can be semiconducting, right? So it can still conduct some electricity, right? So the way that it can conduct some electricity is that there got to be some electrons moving. Okay. So the way it can move is like some electrons. For example, I'm going to use a field ball as the electrons. Some electrons want to can overcome the band gap to be up here. Okay. So then now it's very happy it's in the unfilled state, unfilled band, it can conduct electricity. Okay. So if you move some electrons up there, then you basically leave some holes. So physical picture is like you move some electron up here, you have to leave some empty space behind, right? So these are called holes, or people with H. So in semiconductor physics, people with H plus. However, in our way, we basically use a dot in positive energy, right? So basically, you have the electron. So these are electrons, okay, or E minus, different notations. Okay. So, and also you should never mix this one with this one, or this one with this one. Otherwise, people won't be happy. Okay, in literature, right? So, okay, so. So what I'm going to do is first I'm going to tell you a very simple way of understanding the formation of electron holes. Then we are going to go the harder way in semiconductor physics. Okay. So let me just first tell you the simple way. Okay. The simple way, or in defect, basically I'm going to write here. I don't need this. So basically, the simple way is treating. So basically, we treat electrons and holes. Basically, now as you can see, I'm writing in covariant notations as point defects. Point defect means that we use exactly the same as we talked about just right here using the defect chemical reactions, right? So then we can write the chemical reaction, defect chemical reaction. Before, if we do not form these holes and electrons, there's nothing, right? This is basically everything is filled here, just empty here. So basically nothing. Then we form some electron and holes. So basically we can write something like this. Okay. So we can go ahead and define the fraction of the electrons. Okay. So what does that mean? We know that for any defect, the fraction means that we have ND or big N, right? So ND is basically number of defects, and big N is all the site that it can occupy, right? So then for electrons, we write N. So it's convention that we write N for the number of electrons. Okay. So basically the number of electrons. Okay. Then it has to be divided by all this space it can occupy. Okay. So I just write as NC. Okay. Firstly, what that is, then I'll explain. So it's effective density of states. Or density states, people call DOS. Okay. So if some of you have ever done or ever seen DFT calculations, people talk about DOS every now and then. Okay, what does that mean, right? N. So this needs no explanation, basically how many number of electrons in the system, right? However, we know that it has to be over some the space it can occupy, okay, or size that it can occupy. The size that it can occupy is basically here in the conduction band. So let's neglect the details for a bit. I'm just saying that okay, there's NC. C means conduction band. Electron has to be here, right? Because it's swamped here. There's no space for electron to be here. It has to be here to conduct electricity, right? So basically, so NC is all these sites the electron can occupy. It's basically out there. Okay, so we can go ahead and write this one. It's basically key. Again, another is convention to use the P as number of holes. Okay, and you can guess we have NV. So it's effective. Again, you don't need to know why I call it effective. So you'll find out later. Effective density of states of holes in valence band. Okay. Because again, holes can only be in the valence band, right? So and the site that the holes can occupy is basically NV. Okay. Okay. Now we have this definition. If we apply, it's nothing but this one. Okay. Because we write it as a defect chemical reaction, so we're going to treat it as a defect chemical reaction. Okay. So then it's very simple. Then we write basically this fraction times the fraction of holes is basically some kind of K. Let me write it as KEL because EL for electron or whatever. Okay, it's just a notation. Okay, what this is. So this you have to be a little bit careful. Okay, here you can naturally think that. So to have electron up here, you have to overcome the difference between energy here and here. That's the band gap, right? So basically, then I put a band gap here. Okay. However, band gap is usually conventionally in the unit of EV. EV means electron volt. Okay, so basically you think of one charge and times 1 volt. That's basically 1 EV. Okay. So then when you use EV, what you use here is basically kVt rather than RT. Okay. Again, let me remind you the difference between RT and kVt. R is kV times what? Avogadro constant. Okay. And so if you time 1 eV, you know 1 electron is how much Coulomb? It's 1.6 times 10 to the minus 19 Coulomb, right? So if I time it by Avogadro constant, okay, time it by, of course 1 eV is Coulomb, then it should be 1 Coulomb times 1 volt is basically 1 joule. Then times Avogadro constant is 6.02 times 10 to 23 for mole. So you can do the calculation, right? 1.6 times 6.2 is roughly 10, right? So this one times this one is roughly, it's not roughly, it's 10 to 4, or it's 10 kilojoule, right? So finally you have roughly 100 kilojoule per mole. Okay. So this is basically what I talked about last lecture. It's like 1 EV in, so again, this is in the microscopic picture. Okay, so it's basically 100 kilojoule per mole. Okay, understood? Alright, so let me give you an example. For example, for silicon, EG is roughly 1.1 EV. Okay. And again, kVt at room temperature at 280. How much is this one? Anyway? Okay, so you have to remember this. So 26 millieV. Okay. So then if you solve for silicon at room temperature, KEL should be exponential 1.1 divided by 42. 26 is about 40, right? It's roughly 40. Again, so exponential 40, I just want to give you a number at 10 to the minus 17. 10 to the minus 17. So this number, okay. Alright, it's not finished because if we care about it's basically this guy, right? So okay, I'll erase this part. So if I say, anyway, I shouldn't do that. Anyway, so if we have charge neutrality, so if we do not have any dopant, so we only have electron and the holes, right? So they basically move some electrons from the conduction band to the valence band. Then we should have N should equal to P. Right, so it's very easy to understand. The number of electrons should be the same as the number of the holes to reach the charge neutrality, right? So what does that mean? So we have this should be, this times this one is exponential minus kVt then EG. Okay, so this guy should be N times P over NC times NV, right? You have definition here. No problem, right? Then I just move this one here. I'll say N times P should be NC times NV times exponential 2 kBT EG. Okay. Then if I say these two are the same, then we should have N equal to P equal to square root NC NV exponential minus, sorry, it's kBT, to kBT EG. No problem, right? So this is exactly like the fractal pair we solved, except that now we have this one. Because it can be that NC does not equal to NV. Okay. So in the fractal pair case, the site that we can have the for example the correlating interstitial and column vacancy, we assume that to be equal. Okay. But here, since this connection band is valence band, you can imagine that it might not be the same. Okay. So let's say if we here in the silicon case, let's say if we say, so these are the same, okay. If these are the same, then we know these two are the same, right? If we assume for a minute this is the same, then these are the same. Right, so these are 10 to minus 8.5. Okay, so it's very, very small. Okay, it's, so basically it's kind of part per million level. Okay, so that's why in silicon, if you just take a bare silicon, it's not very conductive at room temperature. So this is the reason. You don't have many electrons or holes in the conduction band or valence band that can do the job. That's the case in metal. Okay, so let's continue. So basically here, so we basically treat the electron and hole as the point defect. Finally, we get this pretty okay approximation or pretty okay treatment, right? So of course, if you want to know more, we have to know the more details in semiconductors. Okay, so I'm going to give you a brief introduction to semiconductor physics. Semiconductor physics for only 40 minutes or so. Okay, so that's basically, I think, all you need to know as an entry level. Okay. So again, let's go back to the picture. So as we can see here, we have the this is the okay. So this is basically the valence band, just like VB here. Then we have the conduction band. Okay, so we know that the electron is going to go from here up to here, right? And of course, the difference in energy is called band gap Eg. Okay, so let me define two other quantities. One is called the EV. This is basically the valence band maximum. This is basically highest level that the valence band has. And this is called EC. So basically, the conduction band minimum, the lowest level of the conduction band. Okay. All right. So in semiconductor physics, what people will define is another thing called an EF. Okay. So I'm going to tell you what EF is. EF is called a Fermi level. 费米能级. How many of you have heard of Fermi level? Only 1, 2, 6轩. Anyway, so I'll basically tell you what Fermi level is. Okay, so this you have to learn just a little bit solid state physics, because we know that electrons are fermions. So in 中文费米子 okay. So the statistics that the fermion apply is called a Fermi-Dirac statistics. Okay, what does that mean? This sounds very complicated. So first, I'll give you a function. Okay, so the function is basically the probability that the electrons or any fermions can occupy the state Fp, or I just write F as function. Energy should be one positive exponential negative. Sorry, there's no negative sign. Okay. So what does that mean? Okay, so imagine, let me draw it here. Imagine is that, so going up, you have higher energy, right? So, and imagine the Fermi level is somewhere here, okay? Do I write a big F? Okay, write a big F. Okay. You can write small f or big F, I mean, in both, okay. So if, let's say I have 0 Kelvin, it's not okay, it's 0 Kelvin, okay. If I have 0 Kelvin, so the kBT is 0, so 1 over kBT is, how much is infinitely large, right? So if E is anyway larger than EF, then this part becomes infinitely large, right? So then F E is basically 0, right? So again, if E is smaller than EF, then this part is negative, right? Negative, then you have the so this is basically minus infinitely large, right? Because 1 over kBT is 0. 1 over kBT is infinite, right? So then F E is 1, right? So this is basically the function, okay. So what does that mean? So if I say, okay, this axis is F, so it's 1 all the time. So it's basically 1 all the time here, and 0 here, okay. So the function is like this, okay. So it's basically 1 all the time, and 0 here. So basically at 0 Kelvin, all the states that it's below the formula, if you have the state, okay. So for Dirac distribution, so this function does not tell you the how many electrons you have. It can tell you if you have state. For example, if I have state here, so if I have orbital here or state here, as you can see, as you can imagine, so in the valence band there are many of the states, right? Then any of the states here, it will be occupied by electrons. So any state up there won't be occupied by any electrons. Simple like that, okay. Questions? No? Okay. So of course we know that we are not at the 0 Kelvin, we are at finite temperature, okay. So we are at finite temperature. Finite temperature means that you have a little bit of leeway, okay. So you can basically, use whatever MATLAB or Origin or Excel to draw this yourself. You'll notice that you have a little bit something like this. Okay. Okay, of course, the higher temperature probably will be something like this. You will basically more and more chance that you have you're going to allow electrons to occupy whatever space there, if you have any space. Something like that. Or if you have state here, it won't be 100% occupied. Okay. Right? Any questions? So remember that in this semiconductors, what you have state here, you have state here, but you have no states in the band gap. Okay, so let's imagine that let's basically join this here to combine with this. Okay, it's not straight anyway. Again, so this is energy. So I mean this is a Fermi level. So if I say Fermi level is here, so this is EF. Again, big F. And then we have the, let's say, the conduction band minimum here. Valence band minimum here. Okay, let's say. Let me draw this a little bit. Okay. So then we need to have something called a density space. This is the density of space. Okay, so these things are not EC or EV. So those are called effective density states. There's a reason for that. So these are just called density states. Okay. So of course you don't have any, so this is basic band gap. Within the band gap you don't have any states at all. Okay, so this is the definition of semiconductors. But directly up and above, above and below, you will have states, right? So band theory tells us the number of density states looks like this. Okay. So basically, so number state. Let's see what I write here. I have a slight problem with the notation. Okay. Anyway, let me. Anyway, okay. Let me put a bar here, just because I want to use it later. Okay. So band theory tells us the density states in the valence band. So basically, this function here, it looks like something like this. Let me write it. I'll explain what that means later. Okay, T. And again, you have. Oh, come on. Sorry. QMH. Let's see. Okay, so maybe some minus like this. Okay, so what does that mean? So if I plug E, so it's function of E. Okay. So this is basically the NVE. Okay. So first of all, it's function of the energy. So basically, if you go down, you have more and more states, right? So if you be exactly on this point, the density state is 0. So if you go down, you have more and more density states. Okay. So right. Anyway, so I can also define. So first I write it, then I will tell you what that means. Maybe we have just anyway. So let's okay. Anyway, let's leave. So okay, it's fine. So here again, the density state is up there. It's basically for the conduction band. Okay, again, if E is equal to EC for the conduction band, again, you don't have any state here. And going up, you have more and more states. Okay, so again, these are just a very simple case to explain semiconductors. Of course, in reality, you have very different. So these are called energy dispersion. So in semiconductor physics, so basically, the density states or DOFs as function of energy. So this is very critical for semiconductors, only for electrons. Okay, you won't have that for ions because this is really from quantum mechanics. Okay, so let's empty start. So we have two other. I mean, this H is a Planck's constant. Planck 常数. Okay. Whenever you have Planck constant, you know that has something to do with the quantum mechanics. Okay. You have other two terms, Me star, Me H star. Okay. So these are effective mass of electrons or holes. Okay. So these can be very different from the. So ME means that it's the mass of electrons. Okay, in the kind of static status. Okay, so when the electron is static, you measure the mass, you get something like this. But these are when you move the electron in the band, you have this Me star and MH star. So these are effective mass of electrons and or holes. Okay. So this is basically to an evaluation of how fast electron or holes can move in the band. Okay. So then things become interesting. So we know that we have state here. We have state here, right? So then the goal is to see how many electrons we have and how many holes we have, because holes can only be here, electrons can only be up there, right? So let's say if we again at 0 Kelvin, now absolute 0 Kelvin, we know that everything above the Fermi level will be empty, right? So every state here will be empty. So every state below the Fermi level will be filled if you have states, right? Within the band gap, you don't have states, but from the EV down below, you have the states. So everything here will be filled by electrons. Okay. Or we like to write this. Okay. So this is at 0 Kelvin. Okay. You can imagine here. However, imagine that if we raise the temperature to finite temperature, for example, we raise the temperature so that we have something like this. Okay. Let me just erase every part. So if we have something like this, maybe just draw a little more exaggerated. Okay. So what you can see is that now here, if you draw the straight line here, okay. Now if you have a state here, you can have some electrons because Fermi-Dirac distribution tells you that here you can have some electrons, right? Because this F is not zero. So here F is not zero, so you can have some electrons. Okay. So we can define the number of electrons. Again, so basically local number of electrons. Okay, that's a function of the energy is NC times Fe. Okay. So basically time this function, which is described here, with this function. Okay. So the end result is you have something look like this. And so basically, if you sum it, these are total n. Okay, so these are number of electrons you have in the system, in the convention band. Again, so if you draw a line here, you will see that here is not 1. Okay, here F is less than 1, which means that here, if you have state here, it won't be fully occupied, right? It'll be not half, a little bit unoccupied, right? So that's the reason you have holes. So because Fermi-Dirac distribution tell you so, okay? So it will look something like this. So this will give you all the holes you have. Okay. So the reason is basically that you have the Fermi-Dirac distribution, you have definite states, then you have this one and this one. Okay. So in our simple calculation or simple treatment, we basically do not differentiate electron as energy, in energy. We just treat it as point defects with the same energy. Okay, we get something similar like that. But 99% this is already sufficient treatment. And if I go on like this, you will see that this treatment is kind of sufficient. Okay. Any questions? All right. So next, I'm going to show why this is kind of correct, why this is acceptable. Okay. Let me erase this part. So what I'm going to do is we want to calculate is basically number of electrons, n. Okay. Because n should be the same as p in this case. Otherwise, you violate electron neutrality. Okay. N is basically now it should be integral, right? Again, so this is you start to have electrons beginning at EC, right? You can, if you go above, you have many electrons. So basically, from EC to infinite, okay. And we know that at a certain energy, we have this many electron density, right? So then we have NC times Fe dE. Okay. You can solve for that. However, if I just use this one, it's too difficult to solve. Okay. So normally what we say, if at the finite temperature, and if kBt is much smaller than T, then E minus EF, sorry. It's much smaller than E minus EF. So what we can do is we can ignore the 1 part, okay? So which means this part is very big. If we have this part is much larger than this one, right? So this part is very big. The is roughly exponential minus E minus EF KBT. Okay, no problem with that. Again, bigger. Okay. Again, here. Okay, so this is called a Boltzmann statistics. So, I mean, you could basically see Boltzmann statistics everywhere, right? So you see this kind of E over KBT here and here, and also in all this chemical equilibrium equation we write about, right? Because it's something quite fundamental. It basically tells you that the states you're going to have is exponentially then negatively proportional to the energy you move away from equilibrium, move away from the EF. Okay. Right, so if we use that, then we can write it here. Okay. You see, then we just plug this thing in. However, when we plug this thing in, we notice that this part is basically constant. Okay, so this part is constant. Let's call it C. Okay. So basically, I write C here, then I have exponential negative. EF over KBT times E minus EC. DE. Right. Okay, so if I define E prime as E minus EC, because otherwise it's too hard to treat, okay, then I can change it to now the lower limit is going to change from zero, right? If E is EC, the E prime is 0. Okay. So what about this part? Now E is E prime plus EC, right? So it's E prime E prime plus EC minus EF. Big F, anyway. Okay. You know that EC is a constant. EC is not a function of E prime, right? So what we can do is we can get the first part out of the integral. Sorry. Okay. Right, so no problem with that. Okay, so, I mean, so this integral you can calculate. Because now there's no EC and nothing else. I mean, you can just calculate it, whatever you can use. I mean, you can probably change a little bit more by denoting another unknown to be E prime over KBT. I mean, that's a trick. But I mean, I think you can calculate it, or if you are lazy, you can use Wolfram alpha or whatever, Mathematica or whatever, you can calculate. So this part is 1/2 pi squared, then KBT, the power 3/2. Okay. Then finally, we have this part, we have the C. Finally, we have then the square 3/2. So this is basically a constant. Basically, I combine the C here and this integral. You get this part. The exponential minus EC minus EF KBT. Okay. So then what I call is basically I call this guy NC NC bar. Okay, so I have to use NC bar because so the same thing as this part here. Okay, the same thing as this part here. Okay, I can do the same thing. I can do the same thing to P. Okay. Let's see where I can find the P. If you, I won't do it again. So basically, P is below EV. You have all the states, right? So you can do from negative to NV, then F Fermi-Dirac or Boltzmann. Depending on what you have. Then V, D. I won't do the calculation, you can do that yourself, but you can imagine that it's pretty much similar to this one. Okay. Then finally you have, anyway, I'll write again. Potential, let's see. KBT. So again, this is the MV bar. Okay. So that's why it's called effective. So effective tensile states or holes. Okay. So then it's called effective tensile state for electrons, right? You can see why it's called effective because this is different from this part, right? So this is function. Okay. So I just write FCT, the function of E. So you can see this part is independent of energy. Okay, that's why we call it effective. Okay. The final thing I want to show you is that, okay, when we get a very simple, we only use like 10 minutes to get something like this. But I spent like last 30, 40 minutes to get you here. Now let's show these two are the same. Okay. So let's show this is correct. Okay. So then we have, again, N should be NC bar potential minus EC EF KBT. You can already see, you can already kind of see where we're going, right? So if you remember, EF can only be somewhere between EC and EV. So EF is closer to EC. You can see this has become larger and larger, right? So basically, if I increase EF to here, so what you can imagine is that this function will basically change from here to something like here, right? So what it does is, like, if you see the states in the convection band, now you have even larger number of electrons, right? Okay. Again, so if you see here, so if the EF is further away from EV, right? So if it's getting closer to EC, it'll be further away from EV. You'll see here for this state, it's much closer to 1 compared to the blue part, right? So this one is much closer to 1. So which means that now you have more states to be filled. The holes will be smaller. Okay, the number of holes will be smaller. All right. If this is getting, you have more and more electrons. Okay. However, we know that what we should have is N should be equal to P. for not undoped semiconductor, if we don't have any dopant. So this is the charge neutrality, right? So then what we have is NC exponential minus EC EF. Okay, anyway, I'm finding myself. KBT should be NV exponential KBT EF minus EV. Okay. So then we can solve for. So we know this. We know this. We know this. We know this. The only we know this. The only thing that we do not know is the Fermi level, right? All right, here. So from the charge neutrality, what we get is okay. Let's see. Okay, so it's negative, negative. So this is actually positive, right? So it's still negative. So what I'm going to do is I move the EF to that side. So exponential 2EF KBT. Okay, then I move this EC to this part. So it's negative here. So move this part should be positive. Should be positive KBT EC minus EV. So what is EC minus EV? So EC minus EV is just band gap, right? So this part is just band gap, EG. Okay. Of course, we have another part which is the let's see. Did I make a mistake? Sorry. It should be. You guys should let me know. It should be plus. No minus, right? It should be plus. You should let me know. Okay, anyway, so I have another term, which is this guy here. Okay. Okay, let's for a minute to say this is 1. Of course, it cannot be, it might not be 1. So this ratio is basically the ratio of the effective mass of electrons and holes to thirds. Okay, so it could be the effective mass for electrons and holes, they are not the same. But let's assume for a minute the same. Okay. Then what we get is basically EF should be 1/2 of EC plus EV. Okay, what does that mean? 1/2 means that they are so basically I get this and I get this then divided by 1/2, which means the EF is exactly in the middle of the band gap. Right, so this is basically intrinsic semiconductors. So EF is in the center of band gap. Okay, you can see from this one. Okay. So that's not finished. So we finish by plugging this back into this equation. For example, we say, okay, we plug in this into this equation, right? So we know that now EF is EC plus EV over 1/2, right? Then this guy is N exponential KBT Now EC minus EV. Now it's EC minus EV. Right? We know EC minus EV is nothing but the band gap. Okay. Okay. So if you compare this one and pretty much this one, you get pretty much the same thing, right? I mean, if you forget that for a minute, of course, what you get is you get this to be correct. Exponential EG over 2 kV, exponential EG over 2 kV. So it's pretty much the same. Okay. Of course, you have slight difference for this one because we already assume that EV and EC they are the same. Of course, you can say, okay, I don't like this. I want to say these are different. You can do that. You can keep going on. Say these are not the same. First, you take the logarithm. Then you time by kV and divide one half. Okay. You can, I mean, you can get this if you plug into this part here. You will get exactly the same result. So what I want to say is that you can see here we only takes 10 minutes, right? So to write something like this. Here, of course, now we know more details and also it's more physics. It's more physical understanding. We spend 40 minutes to get something like this. But they are pretty much the same. So you can take either this one or this one. Okay. So I guess that's pretty much what I will say in this lecture. Of course, on Saturday we meet again. I'll give you yet another explanation. Okay. Before we go, any questions? 用中文也可以。今天这个比较抽象嘛，所以这个回去还是得看看，有什么问题要及时解决。各位有没有问题？何扬州。
听还是能够接受。
但是
怎么用这个就是个问题。
用回头再说。
这听着肯定很爽，就是都是新的，能够听懂。